Good afternoon, everyone, and welcome to today's webinar. My name is Dr. Trevor Townsend. I am the head of the Department of Civil and Environmental Engineering, University of the West Indies, and it's my pleasure to invite today's webinar. It is going to be a very interesting one. We have some very good speakers. We're going to be dealing with the issue of performance-based mixture design. And not only do we have a set of very interesting speakers and presentations, but today we have two former students who are going to be moderating today's session, so that you're in for a very good experience, very knowledgeable, and we hope it's going to be very enjoyable as well. So welcome once again. We're very happy to have you here. Very happy that you could have taken time from your schedules to join us, and we're going to get right into it. So I want to introduce the two moderators, Ms. Kohan Dolce, who is a licensed engineer practicing in St. Lucia, and she is a graduate of our master's program, and her area of specialty is sustainability and transport. And Ms. Nicola Simpson, who's in Jamaica, yet one of our students, and she's a licensed civil engineer in Jamaica, and her specialty is in the area of pavement design and materials. So that I'm happy to have you here, and I'll turn over now to our moderators. Have a pleasant afternoon.
Thank you, Dr. Townsend. Welcome, everyone. We thank you for joining today's webinar on performance-based mixture design. Today, we have 4 presenters. We will have a short question and answer session after the first 2 speakers. We'll direct 1 question at each presenter. We encourage you to post your questions in the chat. Let's keep the chat active. And please let us know which one of the presenters your question is directed at. So we'll move on with today's agenda. First on, we have engineer Lawrence Bridge-Mohan. He's a PhD student in the Department of Civil and Environmental Engineering at the University of the West Indies. His presentation today is on mixture and pavement failures. Engineer Bridge-Mohan, I hand over to you.
Thank you. Thank you, Ms. Dolce. My name is Lawrence Bridge-Mohan. I am a PhD student at the University of West Indies Civil Department. My presentation today is entitled Asphalt Mixtures and Pavement Failures. Just a bit of background, I have been involved in pavement construction and rehabilitation since teenage years. And to this period, I've been involved in pavement material research, pavement investigation, design and construction. Fortunately, during these activities, I have worked alongside the late Mr. Raymond Charles, senior lecturer at the University of West Indies, and continue to work alongside pavement industry stalwart, Mr. Cecil Chin. My presentation today aims to highlight some of the key principles in pavement engineering design that are adopted in practice, as well as to identify the significance of asphalt layers in pavement systems, and to highlight some of the key distresses and responses that we observe in our pavement systems, both locally and regionally. So although a lot has changed since early road construction and the first automobiles, our pavement systems continue to play a pivotal role in the movement of people, goods, and services. With increased economic development and increased movement, these pavement systems are now being required to carry, as opposed to that that was being carried in previous decades. As a result, these systems now need to be durable to withstand increased repetitive loading in its design life. Moreover, pavement practitioners are required to implement pavement systems which meets the demands of its use. In particular, pavement design, the approach is based on combining material layers of adequate strengths in a pavement system which allows for satisfactory levels of service to users within design life, whilst considering the traffic demands and environmental conditions in which they intended to operate. When we look at these pavement systems, they're required to withstand repetitive loading during its design life, as well as to accommodate stresses and strains and incremental damage. These are in response to repetitive loading that are usually within the range of hundreds of thousands to tens of millions, particularly in heavily trafficked pavement systems. One of the oldest and commonly utilized pavement design methods is that of the AASHTO structural number method. This procedure involves the input of reliability, subgrade support, conditions, serviceability loss, and standard deviation data into what is referred to as the AASHTO 1993 structural number equation. The result is the development of a structural number which identifies the structural requirement for traffic loading on this particular, in these particular conditions. A subsequent procedure within this design method, however, involves a layer thickness design method, which has or involves the inputs of material layer coefficients to match the structural requirement for the conditions. This being said, it is therefore very significant that the material layer coefficients that are assumed in the design process are matched with those that are produced for construction in these in-service pavements. For additional analysis, another commonly utilized pavement design method is that of the mechanistic empirical pavement design method. The difference between the AASHTO and the mechanistic empirical is that the output of the mechanistic empirical pavement design method is not the thickness, as would be the case with the AASHTO design, but actually it's more performance based, and output determines pavement stresses and responses. In this particular method, the input into the methods includes the loading criteria, climate conditions, and similar to the AASHTO, layer material properties. A mechanistic analysis provides pavement response in terms of stresses, strains, and deflections, and these are then inputs into transfer functions to determine long-term performance in terms of incremental damage and performance characteristics. So similar to the AASHTO 1993 method, this slide aims to highlight that layer material properties are critical to the design process. As a result, in terms of construction, these materials that are utilized in construction need to meet the criteria to that have been identified in the design process to ensure adequate pavement performance. So for pavement design, when you look at in-service pavements, the wheel load imposed on pavement surfaces causes deflection within the pavement system. As can be seen with this slide, these wheel load deflections causes compressive and tensile stresses within the pavement structure. Notably, if we look at the upper sections of the pavement, particularly in the zone of contact between the load and the structure, the contact area for these imposed stresses are relatively small. As such, the upper pavement layers are subjected to higher stresses and strains, and as a result, need to be of durability as well as strength properties, possession properties to withstand these enhanced stresses and strains. Particularly asphalt layers in pavement structures allow for, because of its inherent tensile strength and compressive strength, allows for accommodating these heavy imposed loads and impose dissipated stress distribution to the lower layers within the pavement structure. In addition to structural requirements, asphalt layers are also required to be tough to wear deformation from the abrasion from wheel and tire loadings. It should provide a smooth, skid-resistant surface and allow for waterproofing of the entire pavement structure. When we look at the asphalt, the different stages in the asphalt mix design process, manufacture, and construction, it is evident that material design requires laboratory analysis. There needs to be controls and quality control and monitoring throughout the entire process. On commencement with the mix design, the laboratory analysis, should encompass determining the material characteristics and its suitability for use. These characteristics include its grading, its shape, geometry, its durability, and its strength. Combinations of the great materials and suitable binders are used to develop optimum combinations to be input into the manufacturing process. When we consider the manufacturing process, controls are required to start within the stockpiling of the materials, including ensuring that these materials that are used for manufacture match that would have been analyzed during the mix design process. In addition, these materials are required to be contaminant-free. And for the process, the mix design process as well, the construction, the manufacturing, the plants are required to be inspected to ensure that batching, proportion, mixing at the required temperatures take place. As a result, controls within the manufacturing and the mix design processes go hand in hand. In terms of construction, we also require to maintain strict best practice in terms of laying and paving. Fortunately, with technology advancements, some of the available equipment allow for grade controls, slope controls, as well as compaction of some of these pavers. As such, the errors are limited in the process. So as we investigate some of the commonly observed distresses and failures that are with our local pavements, I just want to highlight this slide, which identifies an approach that I have adopted in my practice from one of my industry mentors, Mr. Cecil Chin. Basically, it identifies that a distressed road is like a sick patient. Essentially, pavement practitioners need to examine the symptoms that are displayed by this infrastructure. This can be done through visual inspection to determine how the pavement presents itself, as well as for in-depth analysis, we required core sampling, GPR scans, and deflection analysis. So when we examine some of the commonly observed failures within our existing pavement systems, we identify asphalt rotting as one of the more dominant distress responses within our pavement systems. These are described as long-tail wheelpath surface depressions, and as a result of accumulation of permanent strain. They are most evident in areas where there's slow-moving traffic, which produces high stresses and strains within the pavement. Some of the causes for its development include poor mix design, as well as errors in the manufacturing, and we could also have construction practices influence. What are the effects? The effects of these are pavement structure of reduced ride quality, as well as a safety hazard. When these ruts are filled with water, it can provide a safety hazard. In addition, it reduces vehicle safety when maneuvering within these rut structure. Another commonly observed pavement distress, locally and regionally, is that of asphalt shoving. Essentially, this is described as longitudinal displacement across the asphalt surface in a direction perpendicular to the vehicle traffic. These are most evident at some of our heavily utilized intersections, roundabouts, and areas where there are high frequency of accelerating and braking. Essentially, one of the most significant contributors to this development is mix design and manufacture errors, resulting in asphalt mixes of low stiffness. Aggregates shape, binder quality similar to rutting can be contributor factors to mixes which develop asphalt shoving. The result is a pavement of reduced ride quality, and which contributes to vehicle wear and tear to the end user. In addition to structural defects, some of the other commonly observed pavement defects within our roadways are the surface defects. Some of these include the asphalt bleeding, commonly referred to as flushing, which is a mix-related defect resulting from poor mixes. It also provides a skid hazard, particularly in times of rainfall. Similar, polished aggregate results in a surface defect as well. This development results from wearing away of rough angular aggregate particles during trafficking, and is a result of softer aggregates, which are more susceptible to abrasion. The result is pavements which reduce surface friction, promoting a skid hazard to the users. Fatigue cracking potholes are another common defect. These are described as bowl-shaped and generate as a result of fatigue cracking or bottom-up cracking that would be reflected to the surface in the pavement. Environmental conditions as well as traction and vehicle movement on this cracked area result in these potholes developing even further. These potholes actually present vehicle and user safety issues for the motoring public. So in essence, there are a lot of negative impacts from these failures on the public as well as the agencies to repair them. Essentially, these defects produce a reduced ride quality to the end user. They also produce a safety hazard to the commuting public. It results in increased vehicle maintenance costs. In addition, these early failures, when developed within the pavement, result in a reduced design life. Resultant increased pavement repairs are then required earlier in the design life. As such, there is an increased pavement repair costs associated with these. All in essence, there is an emphasis for diligence in material selection, mixed design manufacturing, and construction practices within the industry. In concluding, it is essential to know that roads play a critical role in moving people, goods, and services within our society. Asphalt layers are key components of these flexible pavement structures. The early failures in asphalt layers impacts on both the user and result in increased agency repair costs when they have failed before this anticipated design life. Notably, with the conditions with the COVID-19 pandemic, the road and rehabilitation and construction industry is now required to offer more sustainable, cost-effective, durable pavement infrastructure construction. As such, asphalt mix designers and practices which provide for checking potential distresses can improve the design life and reduce the negative impacts of these. I do thank you very much.
Thank you, Lawrence. Very interesting presentation here. You presented us with some good information. Now we move on to our second presenter, Dr. Derek Gay. He's a geotechnical engineer and also a retired university lecturer. And he will share with us on why we need to collect data. Dr. Gay, on to you. Please share your screen and unmute your mic.
Yeah. Is everyone hearing me? Right. Good afternoon, everyone. The title of my presentation refers to data, but I thought that I would give a background of pavement design and why you need data and to flesh out the various types of models. In the first presentation, we referred to the AASHTO original design, the structural number design type, and then it moved on to the mechanistic empirical designs, and then now that was in 2008 and so on. So I'll just start the AASHTO design of 1993, where most engineers will recognize this from undergraduate. You learn how to develop structural number. Now, what is important here is that none of these parameters suggest anything mechanistic, meaning there's no model associated. The only thing that vaguely resembles a model is the structure form of the pavement itself. But in these equations, they are purely empirically based, regression coefficients and so on. So this was in 1993. In 2004, the initiative started to move to a mechanistic design. And that's the AASHTO Mechanistic Empirical Pavement Design. For sure, they call it MAPD. The last manual I referred to there was in 2008. The MEPD attempts to treat pavement design in a more mechanistic way, meaning you develop a model of failure, physical or rheological model maybe, and you feed it with the various inputs on the left of traffic, climate, pavement parameters, and you invoke these parameters here of stresses and strains and deformations. These stresses and strains and deformations here would then inform the longitudinal cracking, alligator cracking, transverse cracking, rutting, and the measure of goodness is the roughness index. So they still retain the roughness index as a measure of whether the pavement is good or bad. In the early days from 1993, the index of measure was the surfaceability index, right, which goes from 0 to 5. The roughness index is an index that has the number of height of a bump per unit of distance. So we'll come to that in a little while. So this was the approach. I got this from the manual itself. You see all the various inputs here, site investigations, paving materials. So on the left-hand side, it's all about material characterizations and site characterizations. And then in the inputs for design is the climate and environmental analysis and so on, traffic analysis. Climate is important because climate in the temperate countries really, the dominant feature there would be temperature and ice and so on. Whereas if we move to the Caribbean, our climate hazard, so to speak, is actually water, not temperature related at all. Water and drainage, strictly water, landslides, saturation of soils, maybe wetting and drying of expansive clays and so on. So that parameter in this second stage is the most important. Rehabilitation of the pavement, how do we do? We get into distress surveys, non-destructive testing and so on. But so these are common to any method of pavement design, the third area there. This stage 2 of the analysis, well, the way we perform analysis really is to select a trial mix or pavement structure, and then we try to match the material properties to that model of failure. And as I said, the model of failure before was purely volumetric based using Marshall stability parameters and so on. So this outlines the AASHTO mechanistic method. But as I said, the difference is that they're moving towards a more parameters that could be measured as opposed to measured in the field, which relate to distress, right? And the distress parameters, I'll just go through them quickly here. You could get them in the said AASHTO manual of 2008 called the MEPD design. Rut depth, well, it's an empirical parameter here. And one may ask, where is the mechanics in this formula? Is there some model of stress, strain, deformation, time, elastoplasticity, plasticity? Where is it in this equation? It is not immediately apparent because there are no transient elastoplastic models that I know of that captures rut depth and so on. I know Dr. Lee Leon did his PhD recently in that area. So maybe when he comes on, you could ask him about it. Load-related cracking, again, an empirical formula, but it has some mechanistic thing. So they did say that it's mechanistic empirical. They didn't move away from the empirical. So again, these load-related crack, these formulas are based on correlating data. Now, this is important. The data that was correlated here is actually data from testing, laboratory testing. Largely, this is where this is from. This equation is not from a database of failures in the field. They're largely measurements taken in the lab of the particular load test. Some fairly sophisticated tests as well. We move to the reflection cracking, similar equation. Again, these are related back to mechanistic parameters measured in the lab. Some fairly sophisticated measures. I did do some research on the type of testing you would be required if you had to adopt the full mechanistic measure, and I will say straight off that the cost of creating a lab to develop some of these parameters could be prohibitive for us down here in the Caribbean. Right, so we have here reflection cracking and then smoothness parameter, and that smoothness is evaluated through the International Roughness Index. The International Roughness Index has been around for a while. It's based on a mechanistic spring model, a spring and rolling model, and it measures the movement of a pseudo car with a spring and a dashboard in response to various frequencies because of the frequency forcing. And it's interesting that the maximum frequencies here from about 1 to 10 cycles is about the same frequency that you experience in earthquakes. Right. So this is the roughness model. And over here, way back in 1994, I developed a relationship between the roughness index and the then serviceability index. So the serviceability index of 0 to 5 was the original measure, and the roughness index came later, and it had a mechanistic model, really. Okay, I will diverge now into some models that I did just looking at the mechanics of failure, or I will not say failure, deformation, using a very simplified mechanistic model of FEM model of a pavement with asphalted concrete at the top, with a modulus somewhere in the order of about 3,500 megapascals, base of 400 megapascals, sub-base of about 100 megapascals, and subgrade of about 10 or 15. This investigation here of a simple mechanistic model is undertaken to show what is the effect of the asphalt layer failing. You're going to hear a lot more from other speakers about the design of asphalt concrete. So I'm not going to get into the design of the asphalt concrete. But what is striking here is that the asphalt concrete serves as the first interface of the loads to the foundations, which is the soils. And that asphalt layer has a modulus of about an order of magnitude higher than the base and subbase, at least 10 times that value. Now, what I'm going to show is when that stiff layer receives the load, it does a very good idea of creating a sort of a shell and containing the stress in that layer, as you see from this model here. This is the model is a single wheel load, and these are the stresses here. This stress here is 200 kPa, and you can see 200 kPa all the way to 60 or 80 kPa is strictly within the pavement itself. You can see there, right? And the stresses in the base go all the way down to 35. Now remember this number here, 35 is the stress at the interface of the base and the sub-base, right? And up here we are in 200 to maybe 80 kPa. When you look at the horizontal stresses, this is what causes the problem here. You see these horizontal stresses here are right at the interface of the asphaltic concrete and the base course, because there's almost a sharp drop in stiffness across this here. It's like a step function between asphalt and base. And this type of stress strain situation occurs at that interface. Again, when the asphalt begins to age or fail, we will see how that affects how the deformation is affected. If we look to the right of the screen here, you can see my screen is blocked off by the members. If you go over here, I'm trying to get to this. Right. You can see that the stress, and this is, read the stress here as 150, maybe 80 as a negative. Read the white part of the stress, right? So 50 or 40 to 180. You'll see that the maximum stresses are within that upper layer, which is the asphalt layer, right? You see the same thing here. That those peak stresses minus 1,000 to plus 1,000 is within this layer here, and that's the this here now is the shear stresses. Now, these I'm using with shear stress, you know, vertical stress, horizontal stress, and so on. And these parameters, or what should I say, equations, do not appear at all in the mechanistic or the empirical method by AASHTO. They embedded some there in the test, the value of the test, but it's not actually in the equations. Right, so this model here looks fairly straightforward. You may recognize it as looking like the Boussinesq theory. But what I did here is that I changed the modulus of the asphalt, assuming that it had cracked. So I reduced the asphalt modulus from 3,500 megapascals down to about 2,000 megapascals, which means that it's becoming just as stiff as the base course, because when the asphalt cracks and you have alligator cracking, that is what occurs there. And the takeaway here is to see that when that happens, the stress transmits much deeper into the ground. If you see that minus 50 there, that stress goes all the way down to the edge of the base course into the subbase. Similarly, the horizontal stresses actually penetrate into the base layer. Right? So the takeaway from this slide is that when we look at when we soften that shell, that asphaltic shell, the stresses transmit further into the pavement. So we then have to look at so therefore the strength of the lower layers become very, very important. You could see it here too. So this is a failed asphalt or asphalt compromised to half its strength. You could see it's stress penetrated, and you could see that the shear distortion in the layers is also gone deeper, fully embedded into the base course layer. I then changed the model to say, okay, sometimes, for example, in the AASHTO, both in the structural lumber approach and the MEPD approach, they do not look at the actual interfaces of wheels or tires per se. It's not a mechanistic model. So when you look at something, a simple mechanistic model like this, and you put two tires side by side, you begin to see that the stresses, although the stresses overall will be reduced, from the tire pressure, you will still get a much higher stresses going higher into the base course and into sub-base. You could see there from the numbers, we are now up to 65 kPa, whereas we were at 50 or less in the other case. Again, the shear stresses now go over a much wider area here with a double tire load. And that also, when you look at these stresses and so on, one begs the question, how do we represent this in a lab or in a sample? Or where do we represent the sample? Because you get very large contrasts in stresses and deformations, which you will see in a short while. So again, here we still see the stresses contained in that very stiff asphaltic layer. Again, with dual tires, the left tire has a positive stress and the right tire has a negative shear stress. And again, these shear stresses penetrate much deeper than we would like, right, in the pavement design. Right, so this slide compares directly. The upper slide is the intact pavement layer with the 200 kPa on top. And you could see that the asphalt forming very, very well. It's very stiff, containing the stresses within that layer. It's almost like a shell at the surface. When the asphalt is compromised, it begins to look like a normal bituminous, flexible stress foundation where the stresses go all the way down. For example, at the top of the base, sub-base interface, we have 35 kPa. And in the lower diagram, when the asphalt is compromised to 50% of its strength, we have 50 kPa at the same interface. So in design, therefore, what this is saying, we need to consider the full mechanistic form of the pavement before we could go. And the AASHTO 2008 approach attempts to do this. This is just illustrating as well the comparison between an unfailed asphaltic surface at the top, where the shear stresses are well contained within that asphaltic shell. That's 100 millimeter in this case. So, yeah. And at the bottom, in a compromised asphaltic surface, you see the shear shears going all the way into the base layer. You could virtually see the various stress values just from a compromised pavement. And you're going to hear a lot more about design of the asphaltic surfaces. But so I'm looking at over time, if one gets a compromise, we begin to see that the materials degrade, and how do we then apply a simple empirical one-liner model, so to speak, to something like this. This here is deformation, which is interesting. This is just the deformation model of the single tire and the deformation model of the double. The takeaway here basically is if you look at the upper, you see that the deformation is, let's say, forget the value, the number 0.005 millimeters. And with two tires at the same, so the top is 0.0025 and the bottom is 0.0. So you could get 100% increase in deformation. Now what is interesting here as well is that in performance base, we deal more with deformations than we deal with stresses. And what is interesting, therefore, is that the deformations of an experience at the surface of a pavement, actually 90% of it comes from the deformation of the softer materials, which is the base and the sub-base and the subgrade. Because although the stresses are less, the modulus, remember, from the top of this talk, was 10 times smaller. For example, the base stiffness is 10 times smaller than the asphalt. And the sub-base stiffness from my little notes here is about 4 times softer. And it's about 10 times softer as you go from sub-base to subgrade. So when we switch to deformation and a performance-based parameter like deformation, we find that we have to look more at the lower layers, because those are the ones that control what you see manifest at the top as the asphalt ages. So I'll stop here. I just have some quick notes, really, not any hard and fast conclusions. Just stating that we need to have information on our what I call the environmental conditions. In this neck of the woods, in this small territory we call it Caribbean, is English-speaking Caribbean, we have volcanic terrains. Their rocks are hard, their formations could go from hard to swamps, but very, very hard aggregates. In fact, aggregates sometimes are so hard that you can't even crush them. And Barbados and Jamaica has karst terrains, limestones. Jamaica limestone is more massive than the Barbados limestones are more coralline limestones. Jamaica limestones are more sedimentary and, harder, what we call massive limestones. In Trinidad and Tobago, we have a more metamorphic terrains, and that has its own measure of aggregates and problems. So then, well, I'm just make some comments here. We will see later on in the lectures presentation on balanced mixed design, which relates back to the modeling of the asphaltic surface into the base courses. So I just make some comments here really, which you could read. So I think the main takeaway here is to look at the mechanistic models and see how the pavement design is moving away from strictly empirical to a more model-based parameter. But when we go into that model-based, into performance-based design, we need to look at the deformations much more so of the entire pavement all the way down to this subgrade. That's it. Thank you.
All right. Thank you, Dr. Gay. Right. So for those of us who attended UE, this was an example of what Dr. Gay's class is like. Very informative, very detailed. And he gives you the essence of the geotechnical engineering. So right now we'll have a short question and answer session. So I hand you over to Engineer Simpson, who will take us through this.
Hi, good afternoon, everyone. Thanks again for joining. We have a lot of questions coming in. Since we only have 5 minutes for this Q&A session before our next set of presenters, I will be choosing some of the questions, 1 or 2 for each of the presenters we just had. So the first question is for Engineer Bridge Mohan, and the question is, do you think quality control and testing are lacking in the Caribbean? Therefore is a main contributor to more frequent pavement failures?
Thank you, Ms. Simpson. As I would have pointed out in my presentation, the state of the industry is, there are lots of contributing factors. You start with design, material design, structural design, construction, as well as the quality assurance and quality control processes. Yeah, I believe testing has a significant role in addressing some of the concerns and some of the issues that we've been faced with. But it has to be a comprehensive approach to pavement engineering. It has to be looked at in terms of investigation. It has to be looked at in terms of material sampling and testing before you propose a design, a structural design. You need to know what your material characteristics are, because when you input these characteristics into pavement design models, you need to know what these materials can withstand, how durable they are. So in terms of construction as well, you need to make sure that the final product matches the requirements that were made for in the design and the assumptions. So yeah, I believe testing has its role, but it has to go hand in hand in terms with material design, pavement structural design, and the end product quality control and quality assurance.
Okay, thank you very much, Engineer Bridge Mohan. So our next question is to Dr. Gay, and the question is, and this seems to be a burning question, why is seismic design not considered in the design of a pavement structure, and should it?
Oh, that's an interesting one. Why should seismic design? Okay, it's a similar question as to the new wave of treating with retaining walls, how to design retaining walls for seismic. And why I'm going is that a pavement structure is embedded in the ground, right? So that when the ground shakes or moves, that pavement is assumed to move with the ground, right? So you might ask, why do I say that? I'm confident of that. Well, yes, if you calculate the shear wave velocity of seismic waves, and then use that and calculate the wavelength of a seismic wave. If you look at the wavelength of a seismic wave, it's of the orders of tens of meters, sometimes hundreds of meters. So if you go back to my class where I drew those oscillatory waves through a soil, you'd find that if that wave is coming up and the wavelength is tens of meters, the pavement being only at a stretch half a meter thick, there will be no difference in acceleration between the top of the pavement or the bottom of the pavement. It will move all as one together. Even retaining walls up to 6 meters sometimes move as one, because the wavelength of that particular acceleration is of the order of tens of meters or taller than the wall itself. So for there to be an acceleration that would cause shear in a system, you must have a sort of a discontinuity, meaning one part going to the left and the other going to the right. But the wavelength of shear waves takes care of that. They're very long, and a pavement embedded in a soil doesn't really move differentially. Yeah, I think that's it.
Okay, thank you very much, Dr. Gay. And that is something I actually wanted to know myself. So I'm glad that question was asked. We have another minute for Q&A. So I'll give Mr. Engineer Bridgemohan another question, which is, what are the typical periods after construction when distress is being observed in Trinidad and Tobago?
Thank you, Ms. Simpson. It depends. It depends on each road basically would have different responses based on traffic, based on the support conditions. When I would have observed taken these photos, and so some of these roads would have been constructed, I suppose, some within the last 10 years or so, within 10 years or so. So the length of time is dependent on when these will actually occur, dependent on what the pavement is responding to in terms of the conditions that they are being faced with, in terms of traffic loading. So a road that is being loaded excessively is going to probably deteriorate and display incremental damage faster than one which is not as heavily influenced. So.
Okay, thank you very much. So now I'll turn over back to Engineer Dosey, and she will introduce the next two presenters for the next half of our session. Please keep the questions coming in. We have a much longer Q&A session at the end of the presentations. Thanks much.
Thank you, Engineer Simpson. Next on, we have Dr. Fan Yin. He's an assistant research professor at the National Center of Asphalt Technology in the USA. His presentation today will be on balanced mix design approach. Dr. Yin.
Hey, all right. Thank you, Ms. Dorsey, for the introduction. Good afternoon, everybody. It's a great pleasure to be here with y'all, spending 20 minutes to discuss a balanced mix design and kind of like a new era of asphalt mix design that we have in the US right now. Before I get started, I do want to acknowledge Dr. Leo and Dr. Townsend for the invitation. It's my pleasure to be part of this workshop to continue our great discussion on the performance-based mixture design following the great presentations from Engineer Lawrence and Dr. Gay. Okay. Before I get started on the technical part, I don't know how many of people on the call with us today knows NCAT, so I thought it would be good to kind of like spend a minute to introduce NCAT. So we're the National Center for Asphalt Technology. We were established in 1986 as a partnership between Auburn University as a National Asphalt Pavement Association Research and Education Foundation. So we're a research institute that do everything related to asphalt materials, asphalt pavements, asphalt technologies. I'm sure like some of you may have heard some of the things I listed here about NCAT, the NCAT textbook, the technology newsletter that we share the research findings from the research that we do here at NCAT and from other places based on the collaboration with state DOTs and industry stakeholders. And also NCAT test track, that's something that makes us very proud of, give us a great opportunity not only to look at the research in the lab scale, on top of that, we can do numerical simulations on the computer, and also we can apply those in the field experiment to prove the concept. So this is definitely a great opportunity for us to have here at NCAT to bring our research to the next level. And after all, NCAT is a research and education center. So we do innovative, relevant, and implementable research related to asphalt pavement and materials. So now let's get into the detailed discussion or the technical discussion about, asphalt mix design. So why we change, here in the US over the last 20, 30 years, we have been using super paved mix design. And before that, we were using Marshall mix design and Vane mix design. So no matter we talk about Marshall, Vim, or Superpave, they are all volumetric mix designs. So why we change? We have been using that for so long time. What are the limitations about those volumetric mix design? Well, if we go back to look at the volumetric design methodology, the two key parameters in those design approaches are the air voids, VMA, which means the voids in binder aggregate, and the volume of effective binder, VBE. So VBE is just the difference between the VMA and air void. So when we talk about the total asphalt binder that we add into the mix, part of the asphalt binder is going to be absorbed into the aggregate. So they are what we call absorbed asphalt, which do not necessarily contribute to the coating of the aggregate or provide the flexibility or cohesion of the material. So what we are relying on is a VBE, which is an effective binder that is a deciding factor on the durability of the material. But if we look at the VBE, it's a volume parameter. So it gives us an indication about how much asphalt binder we have in the mix. But it does not tell us much story about the quality of asphalt binder. We may argue that this is where we have the binder specification. I know over there in the Caribbean countries, you guys use penetration grading system, and here in the US, we are using the Superpave performance grading system. That works to a degree, but if we have recycled material in the mix, or we started to adding asphalt additives into our asphalt mixture, then just look at the VBE or some other volumetric parameters will not be able to capture the quality of the blended binder or their interactions between the different binder components and additives. So that's why that's one of the main limitations about the volumetric mix design. The other reason why we need to move on from the volumetric mix design is when we look at the VBE or VMA calculation, they are highly dependent on the GSB number, which is the specific gravity of the aggregate, which unfortunately is really not a reliable property. We know the GSB of our aggregates are subject to change over time, but I know here, at least in the US, many states, they do not verify those numbers on a regular basis. So we can have a number used for mix design, but it may not be representative of the material that we produce in the field. If that's the case, those VMA number or VBE number still make sense. And also GSB has a low level of precision, even though this is a well-established standard and there are some precision statement. But even within a small difference that is allowed per the specification, that can have a huge impact on the VMA. In some cases, if I change a little bit on the GSB, I can change from a passing mix design to a filling mix design. So which is very arbitrary and not scientific. And also here in the US, we use a lot of recycled materials, and how we measure the GSB of those RAP, recycled asphalt pavement aggregate, is questionable. About 10 years ago, NCAT did a research to look at all different approach to look at GSB of recycled aggregate. We look at solvent extraction, ignition, or some combination of both. But we could not find a method that worked for all the material that we have. So with that all being said, using GSB as a parameter to calculate the VMA and the VBE has limitations. And also with the volumetric mix design, we don't have a way to know when we add some additive into our asphalt mixture, are they gonna help us in terms of performance, or are they gonna hurt us in terms of performance? I mentioned recycled asphalt pavements, recycled asphalt shingles, recycled tire rubber. That's something we use a lot here in the US. And then we add lots of liquid anti-strip, warm mix additives, liquid anti-stripping, recycling agent, and also polymers. If we add those material into the mix, if we just look at the volumetric mix design, look at the VBE, VMA, we cannot tell their impact on the mixture performance. When Superpave first came out about 25 years ago here, at least in the US, performance test was proposed as part of the volumetric mix design framework, at least for level 2 and the level 3 design methodologies. The researcher at that time, they proposed the Superpave shear tester to look at rutting, fatigue cracking, and the superpave IDT test to look at the thermal cracking or low temperature cracking resistance. There are some equipment purchasing for regional superpave centers here in the US. But the reality is the tests were too complicated in terms of the way the test was run or the data analysis that was conducted. So it was not widely used. So there were only a few like special projects that we apply the test during mix design and during production. But other than that, it's just a piece of equipment sitting in the lab and nobody really used it. And also when superpave first came out, we put lots of emphasis on the rutting. That was the primary distress that our industry was struggling with in the US. I think rutting is still a concern over there. I think Dr. Leon is going to talk a little bit more about that. In order to address rutting issue in the US, we look at the different methodologies. We look at the better quality aggregate in terms of using more angular aggregates. We look at the binder grade adjustment, including like increase the stiffness or increase the viscosity. Look at the polymer modification. This is where lots of research was done to look at SBS, SBR, and some other additives. And we also increase the compactive effort so that we can apply a higher compaction energy to the mix during mix design, try to simulate the higher traffic we would expect that cause rutting issue. And then on top of all these volumetric tweaks, there are some DOTs that implement mixture performance test to look at the rutting. The asphalt pavement analyzer or the Hamburg wheel tracking test are the two examples that has been used. With all these changed, we were very successful. Right now in the US, if we talk to all the most of the state highway agencies, they will tell us that they don't have rutting issues anymore. But on the other hand, we realize we got another problem, which is a cracking issue or the durability issue. In order to address the cracking issue, the state DOTs are now trying to tweak those volumetric parameters. But because of the limitation I mentioned earlier about VBE and VMA, they are volume parameters, they don't indicate the quality. Just look at the volumetric tweaks are not sufficient. So the industry has come to agreement saying like, okay, now we need a more fundamental cracking test that can tell us how good the quality is in terms of resistance to fatigue cracking, to thermal cracking for mix design and production acceptance. With the need on performance testing, that leads us to the development of balanced mix design. If we look at the definition of balanced mix design, it refers to asphalt mix design using mixture performance test on appropriately conditioned specimens that address multiple modes of distress, taking into consideration mix aging, traffic, climate, and the location within the pavement structure. So the way I understand this definition is balanced mix design is a toolbox. In order for us to use it, we need to have some information. The first one is we want to know the project information. Is this going to be in the state of Alabama where we have very hot summer, or it will be in a northern state where they are struggling with cold weather in the wintertime? What about the traffic? Is this going to be on interstate or local volume road? And with that information in mind, we need to have a good understanding about the anticipated pavement distress. Are we concerned about the rutting, or are we concerned about cracking, or moisture damage, or a combination of both? And then we need to select the mixture performance test that can address those pavement distresses, okay? And then with all this information together, this is where we do the balanced mix design. And the end goal is to design a mix that has a better property and has a better chance to give us longer lasting pavement in the field. A very simple way to visualize balanced mix design concept is to look at the optimization of asphalt binder content. We know as we increase binder content, the cracking potential is going to decrease, okay? Because additional binder provides the durability, the flexibility against traffic. On the other hand, if we increase binder content, the rutting potential is going to go up. So it's kind of like a balance between the rutting and the cracking. And then we need to look at the performance test criteria to look at what is a good number that we can accept for a given project. And based on that, there's a minimum criteria, there's a maximum criteria. And then there's a range in the middle that can satisfy both rutting and cracking. Okay, this is where we want to design our mix, based on those performance tests instead of those volumetric parameters. This is just one example using asphalt binder content, but keep in mind that balanced mix design is not only about binder content. There are many different mix design variables that we can play with to improve test results. We can look at the gradation, we can look at the use of modifiers, use of additives, play with recycled material. So there's lots of options that we can modify our mix design to give us a better quality mix, not only in the design phase, but also during production. Right now, there are 4 different balanced mix design approaches. The difference between those 4 are how we require those volumetric parameters, and also what are the innovation potential. Okay, I don't have time to explain in details about each approach, but right now, those are the 4 approaches that has been recognized in our industry. And eventually, we want to go to the 4th approach, the true performance design. In this approach, we want to rely on the performance testing result to make the decision in terms of mix design approval and production acceptance, because those performance test results have better correlation to field performance than the volumetric parameters. I mentioned earlier that balanced mix design, the centerpiece of balanced mix design is performance testing. So if we're concerned about rutting, we need to select the rutting test to use under this framework. There are many different rutting tests available. There's some more fundamental on the left side. The 2 tests in the middle is more like an empirical simulative test. And then we have some purely empirical or monotonic test that can be used for production acceptance, so that can give us a test result in a fairly short period of time. The same thing for cracking in terms of load related, follow the discussion that Dr. Gates said. There's some tests that are more fundamental. The one at the left bottom corner, the cyclic fatigue, it is based on the viscoelastic continuum damage model. Okay, this can give us a true evaluation about the material behavior. But in addition to those tests, there are more tests that are based on index parameters. They can give us an indication about the cracking resistance, but we really cannot use it to predict the pavement performance in the field. So there are some pros and cons associated with each approach, and we need to be open-minded about everything we have on the table. The same thing for moisture damage. If we're concerned about the stripping issue in the field, we need to include a moisture damage test in our specification for balanced mix design. So with all the tests, I quickly show the pictures or with a brief introduction. So how does this work? So if I'm the agency, one thing I need to do is okay, if I'm concerned about rutting, I need to select a rutting test. There are different options as I'm showing here. You can pick one that you have most confidence in and put your criteria in the specification. And then you move on to the cracking. And then there are different tests. You pick the one that you have the most confidence and you are most familiar with, and with your criteria, and you do the same for moisture damage. And eventually, this will be the design criteria that the mix designers or asphalt producers, they need to pass for mix design approval. So right now in the US, there are 11 states that have balanced mix design specification. I highlight them using different colors because they use different BMD approaches. But on top of those 11 states, there are lots of state DOTs that have been doing research on balanced mix design. So with that being said, balanced mix design has gained a much popularity and it's a very hot topic right now in our industry. So if 2 years down the road, if we go back to this map, I'm sure we will have many, many more states that's going to be a balanced mix design states. So what about the benefits of implementing balanced mix design? With balanced mix design, we focus on end products testing instead of specify the recipe requirement. So it provides innovation potential to the mix designers so that they can look into the innovative materials and production technologies for mix design and production. And also it provides a benefit to agencies, based by doing performance testing, rely on the performance parameters instead of volumetric parameters. We have a better correlation to the field performance, okay? So it provides highway agencies with a more reliable way of accepting asphalt mixtures. In other words, we can better control the mix quality that we produce and we place in the field. By doing that, it has a potential to improve our pavement performance in terms of eliminating those poor quality mixes and also eliminating the premature pavement distresses. So some of the closing thought I have here for discussion or for brainstorming with the group here is, I know you guys are still doing a Marshall mix design, but I do think there's a way that we can enhance the mix design using Marshall approach with the BMD approach. We definitely need to look at the performance test. I know rutting is a big concern over there, so we need to have a rutting test. And eventually, with more traffic, with aging of the material, cracking can be an issue. And then we need to select those tests and the criteria based on the field performance data. And then we do some shadow project. We look at how this specification works. And then we need to go back to revisit some of the existing recipe or the volumetric parameter we have. Eventually we want to rely on performance requirements instead of volumetric requirements because, that's the way that can give us a better control of the mix quality. Balanced mix design is still a moving target. There's still some major knowledge gap that we are working on. I mean, this is probably the #1 hot topic in our industry. There are lots of research efforts being conducted on balanced mix design. We have different performance tests available. Do not expect those performance tests to be perfect, but do expect there's improvement in pavement performance after we implementing those performance tests because they have better correlation to the field performance than just look at the VMA and the VBE. In addition to mix design, pavement design and construction are equally important. In order to have success in the field in the future, we need a good mix design, we need a good structure design, and we also need construction. They all need to work hand in hand. So we just cannot focus on one and ignore the others. So we need to look at this as a framework, as a big picture. With that, thank you for your attention and time. I appreciate this opportunity. Hopefully this gives you a quick overview of the balanced mix design. And finally, I want to share that if you guys get the chance to come to the US, we definitely like to welcome you to visit NCAT. With that, I turn it back to Ms. Dorsey.
Thank you so much, Dr. Yin. Very useful information here. And I like the way you ended off success equals good mix plus good design plus good construction. So today our presenters so far have taken us through the empirical approach, the mechanistic empirical approach, and they've also introduced us to the volumetric versus performance-based designs. Our next presenter, Dr. Leon, is a highway, Dr. Lee Leon is a highway and pavement engineering lecturer at the University of the West Indies, St. Augustine Campus, and he will share with us his tips on improving the local mix evaluation. Dr. Leon, I hand over to you.
Thank you. Good afternoon. Thank you, Ms. Dorsey. As Ms. Dorsey mentioned, I am Dr. Lee Leon. I'm a lecturer in pavement and highway engineering at the University of the West Indies. My focus is on pavement materials and performance. So my presentation today will focus on how local mixes can be evaluated using the performance testing, which Dr. Fanyin just spoke about, but in a local context. There has been a global increase in the demand for road construction and maintenance. And as Engineer Bijmohan said, the need for that is because of the increase in the movement of goods and services as well as people. And this has led to an argument that there is a shortage of high quality aggregates locally. Now, many comments and concerns has been discussed with regards to this statement of the shortage of the material. And this has led to people asking questions such as, or making comments such as, these pavement designers do not know what they are doing. because our roads are still failing. Blame climate change for the increase in the in terms of the heat. So that's why we have an increase in the rotting and the stresses in the pavement. We are using the wrong binder. And one of my favorites, our aggregates are marginal. Now, this question of marginal is dependent on the definition of what really marginal is, in terms of an aggregate that is not normally usable because it does not qualify, it doesn't have the quality, characteristics required by a specification, or the aggregate with deficiencies in the characterization because of combinations of improper gradation and other such properties. So we can see that marginal is really defined or dependent on the specification it is written against. So the question is, can the marginal aggregate be used for pavement construction? And the answer is yes. This can be done, and it has been done. And this can be done by allowing the characteristics of the available aggregates influencing your design inputs on your design. Now, just to show how marginal aggregates are really dependent on a spec. For example, we have an aggregate, let's say, meets the requirement of 80 for the base cost of 80% CBR, which we consider very good given the basic requirements for base costs. However, a new specification comes out or a new contract comes out and they require 90% CBR. So automatically, your aggregates which were considered good quality has now become marginal. So marginal is really dependent on the specification the aggregate is being measured against. So with regards to the issue of what is marginal and the specification, some questions and concerns are being raised. And since we are looking to improve the pavement life, these questions should be addressed, but it will not be addressed in this presentation, but these are questions we should have at the back of our minds to have in terms of discussion, whether in-house government discussion, agencies discussion, or private institution discussion. So how are these standards developed? How were they developed? Did we adopt a standard from an international standard? Did the standard, when adopted, did the standard, what materials did the standard use? What data did they use? What climatic conditions did they use to develop the standard? So the question is, should our local standards be rewritten or amended based on the materials we have available? Now, locally, many of our design methodologies consider, the design methodologies for asphalt mixtures consider volumetric properties and strength characteristics of the mixtures, which may not provide adequate insight into the mix performance. Our mixture specification usually includes asphalt content, the VMA, the VFA, stability, flow, air voids, and sometimes density. Now, sometimes one of these properties are not being met in terms of the specification they are being measured against, but does that mean that the roadway or the pavement structure will not perform within its given life? Now, sometimes one or two of these properties fail. Usually the client will reject that particular asphalt mix. So how do we justify the failure of mixtures other than volumetric properties? By adding performance testing or looking at the performance behavior or properties of the particular asphalt mixture. Now, locally, they have added the tensile strength ratio test as one of the performance tests. Now, although it's mostly used for moisture damage tests, it is not adequate to answer the question of mixture performance. Having adequate performance requirements can improve the mixture and answer the question of in-situ performance, thus leading to mixture acceptance. So what other tests can we add locally as a performance measure in terms of the mix design or the asphalt concrete material? in order to get an acceptance stamp on the material used for the pavement structure. So before we actually choose a test, we need to know exactly what the stress is most prevalent in the Caribbean region. So it is dependent, the test chosen will be dependent on the local conditions. In the Caribbean, we have a wet season, which is rainy season or hurricane season, and we have a dry season, with ambient temperatures of as low as 18 degrees Celsius and as high as 32 degrees Celsius. And pavement temperatures as high as 50 degrees Celsius at 11 a.m. in the morning. So therefore, one of our performance tests we could choose or start off with is a performance test that evaluates the rotting potential of our asphalt mixtures. So what is really rotting, or what causes rotting? Rotting can be caused in terms of the asphalt mixture by having low mixture stiffness, having poor gradation of the actually mix, where you have a ratio of cost to fine, the soft binder, whether the stiffness of the binder, whether we have a very soft binder, very stiff binder. Typically, we should use a stiffer binder because of the high temperature we have locally. But as Dr. Ian said, there's a balance between the amount of binder you could use or the stiffness of the particular binder to use for asphalt concrete, because one can lead to the next. So you reduce rotting, but then you increase cracking. Poor construction. Then you have aggregate shape. So you are rounded and angular. Locally, we use an indirect method of selecting the aggregate shape that is required for, in terms of acceptance for mixtures. And what we use has bias in it because we have a person making the recommendation based on looking at the fracture faces of whether this particular particle has 1 or 2 fracture faces. So depending on how you feel or your mood, you might give the wrong answer or categorize the aggregates having the wrong property. So the shift is to move with a more rigid or robust method, which is using a computerized system, which we have available at the university, where you use the AIMS, or you can use any other computerized system that looks at the shape of the aggregate and gives you a value that is not biased. Then you have traffic loading. One of the reasons for rotting is exceeding. So we were designed for a particular traffic loading, but however, we have exceeded that particular traffic loading. So our pavement starts to fail. And then we have the loading mechanism. Is it static loading? Is it dynamic loading or repeated loading? What is the loading mechanism? So what performance tests can be used to actually evaluate rotting? Since we can use rotting as the start of the whole discussion of implementing a performance-based design. So we have the stiffness modulus, or what we know as the resilient modulus in our structural number or the actual design. So typically we have a resilient modulus that is used in pavement design. Now, I have seen, and also engineers usually adopt a layer coefficient value based on assuming that an asphalt layer or asphalt material has a stiffness of 420 KSI or 3000 MPa. However, we have seen that the ranges of stiffness we actually get locally are between 1600 to 2200 MPa. So we can see that this will affect the pavement design as well as the behavior of the pavement. So just for an example, comparison between the two, what we adopt and what we actually, the true nature of the pavement and materials we have. So we adopt a value of 3000 MPa for the surface. And we have a given traffic level and we design. And then we move on to the actual values we have for the asphalt layer, the asphalt material, which is much weaker than what is adopted. So we have 1800 MPa as the example here. So we can see that the difference is the asphalt layer, surface layer would be will be thicker and thus will be more expensive. However, we have to balance the cost as well as the life of the pavement to know what should be the right thing to do or in terms of the selection of the pavement structure. So we have the construction cost of what is adopted is much lower than the construction cost of using or pavement design that is based on the actual properties of the material. However, the adopted design will have more maintenance, and the maintenance cost will be much more because what we have is what we design for. This is not what the material actually characterized as. So we design for 3000 MPa. However, our design, the material strength is actually 18,000 MPa, 1800 MPa, sorry. So we can see that the pavement structure will be thinner, but however, the pavement structure will not be able to withstand the loading. So we have more maintenance to do on the adopted design as compared to less maintenance and a wider gap between the periodic maintenance. So this we can see that in terms of the life of the pavement, the cost, maintenance costs will decrease, and in the number of maintenance procedures or even the methodology, what type of maintenance to do, will increase if we have the adopted design with the wrong values or the wrong inputs of the actual materials we have looked at. Another performance test that could be added. So we have the stiffness to give us the stiffness properties of the material. Now stiffness can be improved with the type of binder we use. We can move to using a stiffer binder. So moving away from a penetration grade of 60-70 or 60-75 to probably 40-55 or somewhere in between. This will come with some research and so on. So we have the wheel track test or the repeated load test. Now, either of these tests can be used. However, my view is easier to use the cylindrical test, which is the repeated axle load test, because it's easier to core the sample than having the wheel track where you need a slab sample. So if you have to get a field sample, you actually have to cut a slab, which is more difficult as compared to just coring out a cylindrical sample. Now, both will give you the permanent deformation strains or the rotting depths of the after number of loading. All right, so or number of loading cycles. Now, this test can be done at varying temperatures, so we can actually run this test at the ambient temperatures or higher temperature, pavement temperatures, which we experience in the Caribbean region. Now, the test also, in some way or form or fashion, can correlate with the mechanistic part or performance checks in the mechanistic design, where you look at the rotting percentage, the total allowable rotting, and the cracking percentage. So we can actually, some way or some form of fashion, we can actually correlate these values from the laboratory test to the field performance as well as to the mechanistic performance in terms of the design. So from Dr. Ian's presentation, what framework should we adopt or implement or have some discussion on? Which performance-based framework should we adopt? I think we can start locally with the volumetric design with performance verification. So we are not moving away or completely ignoring the volumetric design methodology. So we use the design methodology, the volumetric design methodology, which is the Marshall we use locally, and verify this with performance test or performance properties. So after you have done your volumetric design and you have passed all the requirements, you move on to doing a rotting performance test, or if we select a cracking test, any of the tests. However, if it fails, you go back to the volumetric design and you redesign the mix. Now, this volumetric design, we should have some flexibility or some relaxation of some of the criteria. Because sometimes when you go back to the design, you might have to relax on the criteria to actually have it in terms of when you go back to the performance test to pass. So now the idea is to have research to support which criteria to relax, whether it's the VMA or whether we are relaxing the VFA or any other volumetric requirements that is needed for the design or the project. So after we have passed the performance test, you then move on to the moisture damage test, which is what we use the TSR, which is part of the performance test used locally. And then after that, we can see that we have accepted the particular asphalt concrete mixture. So remember that volumetric properties would have to fall within the existing local specification, or if we have amended the specification. Now, the shift of adding performance tests may require pavement designers to not only use the structural number procedure, but complement that or add the mechanistic design as a new focus in terms of pavement design. However, moving in this direction will require more research in calibrating some of these design tools using properties of local conditions, the material, and so on, as well as using both laboratory data and field data to achieve this goal of moving to a performance-based design. So why the need for a balance of performance-based design framework? One, the problem is we cannot rely only on volumetric properties to inform us on the in-situ performance of a pavement, asphalt, a flexible pavement. And the benefits of the new approach, it recognizes the performance issues related to the composite material or the composite mix, increases the understanding of the factors which drive mix performance, design for performance not just to the spec, and start thinking outside the long-held rules and constraints of a specification or the volumetric specification. And also, there is some innovation that can be done in terms of the mix design. So the contractors can actually be a bit innovative in coming with a mix that actually performs well and can increase or improve the life of the pavement structure. So just giving you a brief on the research that has been done locally at the university in our department. Some have been completed and some ongoing. One of the areas we look at is the impact of the coarse aggregate type, angularity on the deformation or the rotting of asphalt concrete. So we have done a lot of asphalt concrete research. So one of the outcomes of this research, some of the outcomes are a development of an equation that predicts rotting or permanent deformation, strains with the inclusion of aggregate shape properties. We have also highlighted the ranges of confinement stresses that should be used in evaluating asphalt concrete in a triaxial setup, because there are varying values when you look at literature or when you look at different countries of what is the confinement stress that should be used in evaluating asphalt concrete. Also, the location of the neutral axis between compression zone and tensile zone, which Dr. K mentioned about the asphalt layer experiencing both the compression and tensile behaviors. So it is always good to know where is that neutral axis, where is the division between compression and tensile, to know if you are doing any improvements of reducing cracking in a pavement structure, you will know exactly where you can place whatever mechanisms or application to reduce that cracking. So knowing where the tensile zone is, what the limits of the tensile zone is, you will know whether you will actually improve that resistance to cracking. We have also looked at sustainable asphalt concrete and sustainable material and stabilized material. So we have completed and also ongoing research in recycled asphalt pavements in stone matrix asphalt, the use of recycled concrete waste in stone matrix asphalt, and on ongoing research currently, the combination of these two recycled materials in an HMA dense graded mix. This will reduce the cost because you will reduce the percentage of virgin aggregate you have to use. And improving the characteristics of bitumen stabilized material, and also stabilizing clay, expansive soils with limestone dust and recycled concrete fines. So just to close, we are at the department open to partnering with industry in doing research that improves pavement and road infrastructure. And we welcome discussion with any government or private agency in this regard. So thank you again for giving me a few minutes of your time.
Thank you, Dr. Leon, and I'm happy to hear, and I hope everybody else is happy to hear that the department is up for discussion with local agencies, contractors, labs, government agencies, and so on as to how to improve our local mix design. Lee, I noticed you generated quite a few questions with your presentation. So I will now hand over to Engineer Simpson, who will take us through those questions. During this question and answer session, we will direct questions to all of the presenters.
Okay, thank you. All right, so I'm going to ask all the presenters to keep your cameras on so that if the question is turned over to you, we'll see you when you're answering. Okay, so I'll start with a question for Dr. Gay, and I have many questions I will be giving to each of the presenters, and whatever questions we fail to be able to answer during the session based on our time, we will try to provide answers to you all after this webinar via email. So my first question goes to Dr. Gay. Should pavement layers really be drainage layers given the weak properties of some of the subgrades in the Caribbean?
Right, well, that question kind of answers itself. Drainage layers are meant to be drainage layers all their life. That's the default of a granular base. That's what it was called, granular base course. So yes, if that drainage layer does not remain porous through its life, through its stress, strain conditions, then it should not be used as a base course. That's as simple as I could put it. Those drainage layers must be base course must remain as drainage layers through stressing and compression and stuff like that. Yeah.
Okay, thank you, Dr. Gay. For Engineer Bridgemohan, are there any common factors or shortcomings in pavement designs that contribute to most or all of the pavement failures experienced in the Caribbean?
Sorry, can you repeat the question, please?
Sure. Okay, so the question is, are there any common factors or shortcomings in pavement designs that contribute to most or all of the pavement failures experienced in the Caribbean?
Thank you. Yeah, I would say, as I indicated in a question earlier, I think we need to look at the entire pavement cycle in terms of when we propose a solution, we need to do an in-depth pavement investigation to determine exactly what is the problem and what conditions exist there before we propose a actual pavement design. So I think that it may not be as shortcoming in all areas, but it is something that we should probably emphasize on, as well as because if we know what exists, we should be able to come up with a more reliable pavement design in terms of what could withstand the stresses and strains that are going to be anticipated.
Okay, thank you. All right, thanks much. The next question is for Dr. Yin. What aspects of a mix design are sensitive enough to throw off a mix with small changes?
Can you repeat the question, the first part of the question? I don't think I get the first part, so.
Sure. The question is, what aspects of a mix design are sensitive enough to throw off a whole mix with a small change?
Okay, yeah, I think that's a good question. Depending on when we talk about mix design, we're talking about which approach, right? If we're talking about the Marshall design, I believe that's what you guys are using over there. It's pretty much based on the volumetric parameters. I would say, like, I mentioned in my presentation that aggregate specific gravity is a key, since, that's kind of like a driving factor for the VMA, which is what the agency is using for acceptance. So that can be a parameter that a small change that can throw off a mix design, completely from passing to fill or the other way around. And when we do balanced mix design, which we put more emphasis on the performance testing, one thing I realized over the last several years of research is binder quality. So we can have the same binder. We can have 2 or 3 binders. If you run the penetration or superpay PT grade, they have the same grade, but they give us very different mechanical properties when we run those rutting or cracking tests. Because some of the parameters we are looking on the binder scale, they are empirical. They do not capture the real rheological parameters of the asphalt binder. So that's one example of the balance mix design that can change everything. So we can have a good mix design, but if we switch binder source during production or from design to production, your production number may not look as good as you expect. So that's, hopefully that answers the question.
Okay, thank you. Thank you, Dr. Yin. Next question goes to Dr. Leon. Will the department be providing training on BPMD? That's performance-based mix design.
Good question. We would be happy to. However, we will know the results of the survey, whether it's, we'll take a decision whether we can provide this based on the number of persons actually wanting that particular training. It will be an initiative that we'll welcome. I'm pretty sure Dr. Thompson will welcome that. Yes, so yes, I would say yes, depending on the response of the survey. The survey they will get at the end of the webinar.
Okay, thank you.
Just to add, Nicola, we are looking at courses in pavement design, pavement construction, because our engineer, Rich Mohan, mentioned the construction, and Dr. Yin mentioned the importance of construction. And we are looking at those kind of courses as courses to be offered to practitioners and design and construction engineers in the very near future. So yes, we are looking at those as short courses that engineers can come in and do some upgrade. So that is something we're looking at. Thank you for that question.
Okay, thank you, Dr. Townsend. That is very good news. I should be signing up for some of those then. All right, so the next question is actually for you, Dr. Townsend. The Ministry of Works in Trinidad planned to install weigh stations to monitor truckloads some years ago. This is a two-part question. First part is, what is the status of those weigh stations? And is the data available to the public to assist in pavement design?
Well, I am not a spokesman for the Ministry of Works, but as far as I'm aware, there are no weigh stations on the major highways of Trinidad. There are areas where weighing is done, and there are some consultants who do for projects, measurement of weight of trucks. The experience that they have had indicates that trucks are still being significantly overloaded. Somebody asked a question about other types of vehicles in terms of the impact on the pavement, but really the life cycle of life cycle of pavement does not depend really on the number of private cars that use the pavement, because they do not create that stress on the pavement that Dr. Gay was speaking about. But those high stresses on the pavement are on the basis of the truckloads and the truck axles. And in particular, overloaded truck and overloaded axles have a significant deleterious impact on pavement life. And that is something which is ongoing in Trinidad, and I suspect in several territories as well.
Okay, thank you. The second part of the question was, are there any mechanisms in place to monitor axle loads for other types of vehicles besides trucks?
Well, that answers the question. Essentially, in terms of axle loads of other types of vehicles, they're not really significant in terms of the impact on the pavement structure.
Okay, thank you. Thank you, Dr. Townsend. Going back to Dr. Gay. Next question for you is there any data that could supplement the improvement of pavement designs that we currently have trouble collecting in the Caribbean? And do you know if solutions for this are being looked into?
Data, collecting data for pavement design, I suspect they mean the mechanistic pavement design, or, well, There's no, what should I say? There's no database that I know of that people put up or where we could draw on. Most times I've worked around the Caribbean and look at aggregates in St. Lucia, Jamaica, Barbados. They actually come from private enterprises and doing tests on the various aggregates. The Ministry of Works in various islands, most islands have a lab testing facility that I know of. But a lot of the times their testing is very, very limited, mainly to grain size, distribution, maybe plastic limits and so on. But very few people do stability, for example, or hardness or early abrasion, that kind of stuff. I don't know of that, let's say in Barbados, or even in Grenada or St. Vincent, St. Lucia. I don't know if they're doing that up there. Unfortunately, there's no real database. And here at UE, I mean, Dr. Leon could bear me out on this. When Mr. Charles, late Mr. Charles was around, we actually had a subscription to foreign journals where they gave us criteria for materials, and everybody really did their own thing. Unfortunately, we never really collected and collated a database of materials. I think part of the reason is that people tend to use that detailed information to competitive advantage, and they wouldn't release it very easily. And sometimes they even debar you from sharing it. Other times they don't really want you to know the real deal about their quarry, so they tend not to share it. So yeah, we don't have a database, unfortunately. I don't know if Lee wants to say anything that maybe you're collecting or somebody could create a database somewhere.
As you said, we really do not have a database. That is some of the one discussion I've been having with Lawrence, is the need for us to have laboratory data as well as field data, because there is field data is lacking in terms of asphalt pavements in the Caribbean region. One, we do not even keep historical data properly, so we don't know 10 years ago what we actually. So a road was designed and built. You can asking somebody what binder they used 10 years ago, you don't know, because you have no data on the records. So now when you have to do, let's say we have to use this material for recycle purposes, we really do not know what the original binder was, what the original aggregate was, whether it was limestone, what it was andesite, what it was. So I think there is a need to actually start that idea of collecting data, but the logistics of it is a little more difficult than just saying this is how it sounds.
Okay, thanks much, Dr. Lee. Next question goes to Dr. Yin. How does the wrap content affect the performance-based mix design for asphalt mixtures?
How does it what, sorry?
How does the wrap content affect the performance-based mix design for asphalt mixtures?
That word is eluded. The rock content.
No, wrap, R-A-P.
Wrap.
Like
That's what Dr. Fan.
Wrap content? What is it, wrap content? Maybe I lost that.
Recycle asphalt pavement.
Or recycle asphalt. Oh, I think that should go to Dr. Mr. Bijmohan. He's a recycle asphalt specialist. I don't, but that, well, let me give my answer and then I think Mr. Bijmohan. Recycle asphalt really is in the domain of those guys who do it, and it's a very specialist thing based on specific tests. I don't know that there's a generalized answer to recycle asphalt. I will defer that to Engineer Bridgeman.
Thank you, Dr. Gay. I think this question is actually an asphalt-related question. I think Dr. Yin would have a lot of information on, so I think I'll transfer to him. Thanks.
Okay. Yeah, I'll be glad to take this one. That's a good question. I mean, that's one of the questions we got asked a lot when we were talking about balanced mix design or performance-based mix design here in the US. I think there are two parts. The first part is, because the asphalt binder in the wrap, they are more heavily aged than the virgin binder or the new asphalt binder we're using. So when we add the wrap into the mix, it will provide some higher stiffness, which will translate into a better rutting resistance to some degree. This is a bonus, right? But on the other hand, because asphalt binder are more heavily aged, they don't have good relaxation properties. So they will have a detrimental impact on the fatigue or thermal cracking resistance. I know thermal cracking may not be an issue over there, but fatigue cracking, either top down or bottom up fatigue cracking. So it's kind of like, it has some benefit, it has some challenges. So we really need to do engineer in terms of wrap content when we do the mix design. There's some, on top of wrap content, there are some additive that can be added to rejuvenate those asphalt binder in the wrap. This is another topic. It's more about, the chemical, about the asphaltene, maltines, but there are some ways that we can reuse, better use recycled asphalt pavements without having the, durability or cracking issues. But, just to answer the question is wrap will improve the rotting resistance or the stiffness, but it will reduce the cracking resistance of our asphalt mixtures.
Okay, thank you very much, Dr. Ian. Very good answer on that. Next question goes to Dr. Leon. You spoke about stiffness properties and measuring it using laboratory tests. If an agency cannot spend millions to upgrade their lab, what can be done in the interim to estimate that resilient modulus value for input in the pavement design?
That is a very interesting question. Well, it's okay. I will say what I did for my PhD is I developed an equation for the prediction of permanent deformation with the inclusion of aggregate angularity. What agencies can do, as well as countries within the Caribbean region, is getting samples or getting the plants or contractors who have been constructing pavements to get some samples, some core samples, get the information of the mix design, get the information of the aggregates used, and an equation can be developed based on all these properties there to obtain the stiffness. Because we can take these samples, measure the stiffness values, and give an idea of given an equation, that could be used to at least give an estimate of stiffness value they could use locally. So each country, I'm pretty sure there are more than 20 contractors doing asphalt pavements, which you can get over 1,000 samples with different mixes, different combination of binders, different combination of aggregates, and so on, and develop an equation which can be used by contractors, by engineers, where they can simply put the information in, what they get from a volumetric test, and give an estimate of the stiffness. So at least it will not just be adopting a value, but having an idea of predicted value with as much, as the least amount of errors as possible in the equation, but at least having a value they can use that actually tells you your story of the actual material you have locally. So this is my answer in terms of how they can reduce or avoid spending all the monies and the millions in buying material or buying equipment to actually do the measurement or the performance testing of stiffness.
Okay, thank you very much, Dr. Leon. Next question to Dr. Gay. In La Brea, the paved roadways do not maintain their form. Any ideas as to possible solutions?
Your mic, Dr. Gay, your mic is off.
Sorry. Yes, the La Brea situation is unique, right? It's along the pitch lake. It's an active pitch vent feature, geologic feature. And plain and simple, all the roads along the pitch lake, they actually move. And they pump water and pitch to the surface. So the only way we did some experiments on them many years ago in small areas, and the only way to derive a pavement of any long to solve that deformation problem is the bridge you'll solve with like slabs or something like that. In the US they use a lot of concrete pavements, for example. So if we had the funds, we could use a CRCP type pavement in that area, continuous reinforced concrete pavements. We don't use that in the Caribbean, but But certainly flexible pavements, which is what we design typically down here, would not work there. You just have to follow the roll of the land because it's not going to stop. It's been moving consistently for 100 years and more. And I know there have been many efforts, including some I've been involved in, where we tried aggregates of different sizes and so on, and the asphalt just flows into the voids and just distorts. And when you squeeze one area, then it pops up in another area. So I really can't say that I have an answer for that Labre area at all. It's a unique problem, and we just have to live with it in a sense. Yeah.
Okay, thank you very much, Dr. Gay. Hopefully with these continued webinars, we'll have some engineers coming to help with this issue. All right, so the next question is for Dr. Yin. Has the NCAT done any research into the adjustment of pavement design inputs to account for future and current climate change environmental conditions, such as colder winters and warmer summers?
Yeah, we had done quite a bit of a structured design on our NCAT test track, not only to look at the asphalt, design approach that, Lawrence talked about early, and also the MEPDD approach that Dr. Gay talked about early. But one thing I want to mention is because the location of our test track, we are in the state of Alabama, so we really don't have, cold winter. So that's something we can now simulate. We can simulate lots of things. We can apply accelerated loading on the pavement, but the climate is what we have here. We just cannot simulate that. But with that being said, we starting in 2015, NCAT did partner with the Minnesota DOT. They also have a testing facility there in Minnesota, which have very cold winter over there. So thermal cracking is a big concern. So we collaborated together to look at the structure design, the mechanistic response of the pavements. We do have lots of data in terms of publications or reports. I believe we have many reports available on the NCAT website. So I do recommend for those who are interested in getting more detailed information to access from there.
Okay, thank you very much, Dr. Yin. And we just have a few more minutes left. I'll ask two more questions. The next question goes to Dr. Leon. It would be very useful for Trinidad and Tobago and the wider region to have a research and testing facility such as the US NCAT facility, considering our TLA, or is it better to forge partnerships with such institutions?
It's an interesting question. And I actually asked that question to Mr. Charles when he was alive. His answer was, it would be nice to have it, but one, which country in the Caribbean would be responsible for the test track? That was the major problem. Who's going to be responsible for it? It's like having a World Cup team of the Caribbean. Who's going to have the most team to coach and so on. So it would be nice to have it, but the logistics of it is a little difficult. So we have to resort to actually doing in-house, which is doing each country doing their own, probably a test track on one of the roads or so on, at 200 meters or something on a particular road constructing, and record data, take data for probably the next 5 years, or because we really do not have the equipment to do the accelerated loading, where we can increase and have, in a short period of time, have 2 million axles, 5 million axles, and so on. So that's the only way we can actually address in terms of a test track or some sort of field testing. So that's the only way we can do that locally.
You can just add to that before you go on. We are actually in current discussions with NITCO, who are planning to put down about 5 test strips in some of the current highway construction programs, so that there is going to be a process of at least looking at trying to get some field data over the next 5 years in terms of the performance of alternative pavement designs. And UWI is actively involved in both the indication of what should be the suggested structural designs, as well as making recommendations in terms of the continuous monitoring of performance. So that's a start in the right direction.
Okay, thank you very much, Dr. Townsend. We have another question, which is now our last question. And this question goes to Dr. Gay with regards to the mechanistic approach. And specifically, this person who's asking is from Belize. And the question is this: is the mechanistic approach restricted only to the asphalt layer? What about the base and sub-base layers? For example, in Belize, most, if not all of our roads are surface paved using chip sealing due to economic and extensive local use. However, we experience the same problems, that is potholes, rotting, etc. Can the mechanistic approach be applied to all layers of the pavement structure? Not hearing you, Dr. Lee, your mic. Sorry, Dr. Lee.
Yeah. Yes, the answer is yes. In fact, the mechanistic approach was actually conceived to treat with that problem. Let me explain why. The original structural number approach was heavily weighted towards the asphalt layer. That produced the highest structural number value in terms of your final outcome. And that has a shortcoming in that, as I showed in my presentation, that it has such a high stress discontinuity between the asphalt and the next layers that as soon as that goes, your entire pavement collapses, basically. But the mechanistic approach, yes, allows you to put parameters into the base and sub-base layers and even into the subgrade. Whereas you could put your greater strength in the base material, should you have those materials, like for example in St. Lucia, in there, and put the strength also in the sub-base layers and use a very thin veneer of asphalt, for example. So if in Belize they have that type of materials, yes, you can in fact work out a rutting model and a deflection model and strength model based on base coarse materials. And in fact, over the Caribbean, we should be going in that direction. And I think that we should embrace that mechanistic empirical method. Because a lot of our aggregates surpass, for example, the original structural number method uses CBR of 80, let's see, that's just a number everybody goes for. But I am sure if I go in Tobago or in St. Vincent or St. Lucia, the aggregates there by way of CBR is over 100, you know what I'm saying? It's so hard you can't even crush it in a sense. Well, you could if you blast it. So we here should optimize our materials, you know, we should optimize the materials that we have and use the base course. And that the mechanistic method allows you to characterize those base and sub-base materials all down to the subgrade successfully. So the answer is yes, and I will advise that you do it. So the mechanistic MEPD method is a viable solution, and I think we should actually go towards that methodology.
Okay, thank you very much, Dr. Gay. We've come to the end of our question and answer segment. And before I turn over to Dr. Townsend for the closing remarks, just reminding you all that there is a survey that we'd love for you to fill out. The link has been posted in the chat. This is survey on highway agencies, testing labs, and contractors. This information would be very, very useful to us. And the questions that have not been answered in our Q&A section the answers will be sent to you sometime after this webinar. So I now turn over to Dr. Townsend.
Thank you very much. Thank you very much, Nicola, and fantastic job on our part of our moderators. I think that we've had a really interesting and powerful webinar this afternoon. I want to thank our presenters, Engineer Lawrence Bijmohan, Dr. Derek Gay, Dr. Fanyan, and Dr. Lee Leon for very thought-provoking and thoughtful presentations on a topic which is of tremendous interest and value, because in terms of infrastructure spending on roads and roadways is a significant part of almost every country's, at least in this region, government infrastructure expenditure. It is certainly the biggest expenditure, so we need to make sure we get it right and not waste it. So I want to thank our presenters for coming forward with this, the content of their presentations and the quality of their answers. I want to thank our young moderators. I'm very proud that the University of the West Indies Department of Civil and Environmental Engineering has been able to produce graduates like Ms. Kohan Dosi and Ms. Nicola Simpson, who can handle themselves, who show a level of maturity and dignity that is important in terms of our profession. And I really am very happy to have seen them perform today. I want to thank the Marketing and Communications Department, and they have been so helpful in putting together this webinar. They have been so helpful in terms of their advice and in making available. And we will be having the recording of today's session available, as well as we will be giving you answers to all those questions which we could not, because of just the time constraints, we couldn't answer. And I want to thank you all attendees. We have had over 120 attendees. It shows a tremendous amount of interest. And I want you to look forward to further webinars that we are going to be developing. We have another at least 2 or 3 webinars in the next couple of months coming out of the Department of Civil and Environmental Engineering, Faculty of Engineering, University of the West Indies, St. Augustine. And we do look forward to you joining us at our next webinar, where we will have another interesting and thought-provoking topic. Thank you very all, and have a good day, everyone. Thank you and goodbye.